Welcome to i9 Global. Join us as we explore the foundations of artificial intelligence. Today, we'll be diving into the topic of deep learning. Deep learning is a subset of machine learning that employs artificial neural networks with multiple layers to automatically learn complex patterns and representations from vast amounts of data. Unlike traditional machine learning approaches, which often necessitate manual feature engineering, deep learning has the remarkable capability to autonomously extract features from raw inputs such as images, audio, and text. This ability to learn directly from unstructured data is a game changer in the realm of data science and artificial intelligence. The architecture of deep learning models typically comprises numerous interconnected layers, each designed to transform the input data into increasingly abstract representation. The initial layers may identify simple features, such as edges in an image, while deeper layers can recognize complex structures, such as faces or objects. This hierarchical learning process allows deep learning models to achieve high levels of accuracy in tasks such as image classification, speech recognition, and natural language processing. One of the most significant advantages of deep learning is its scalability. As the volume of data continues to grow exponentially, deep learning algorithms can leverage large datasets to improve their performance. This scalability is particularly beneficial in domains like healthcare, where vast amounts of patient data can be analyzed to identify trends and make predictions about disease outcomes. Similarly, in the field of finance, deep learning can be employed to detect fraudulent transactions by analyzing patterns in transaction data that would be nearly impossible for humans to discern. Moreover, deep learning has the potential to revolutionize industries by enabling real-time decision-making. For instance, autonomous vehicles utilize deep learning algorithms to interpret data from sensors and cameras, allowing them to navigate complex environments safely. In customer service, chatbots powered by deep learning can understand and respond to customer inquiries with remarkable accuracy, enhancing user experience and operational efficiency. Despite its transformative potential, deep learning is not without challenges. The requirement for large data sets, significant computational power, and the risk of overfitting are critical considerations that practitioners must navigate. Furthermore, the black box nature of deep learning models can make it difficult to interpret their decision-making processes, raising concerns about transparency and accountability. Basic concepts in deep learning. Deep learning models are inspired by the structure and function of the human brain, where each neuron processes inputs and passes the output to the next neuron. The key idea is to use multiple layers of interconnected nodes, neurons, to gradually learn more complex representations of the input data. This layered architecture, often referred to as a neural network, allows for the extraction of intricate features from raw data, enabling the model to perform tasks ranging from image recognition to natural language processing. At the core of deep learning is the concept of hierarchical feature learning. In the initial layers, the model identifies simple patterns, such as edges or colors in images. As the data progresses through subsequent layers, the model begins to recognize more abstract features, such as shapes or textures, ultimately culminating in a comprehensive understanding of the input. This multi-layered approach mirrors cognitive processes in the human brain, where higher-order thinking emerges from the integration of simpler sensory inputs. Convolutional Neural Networks, CNN. One of the most significant advancements in deep learning has been the development of convolutional neural networks, CNNs, which are particularly adept at processing grid-like data, such as images. CNNs utilize specialized layers that apply filters to the input, allowing the model to focus on spatial hierarchies and local patterns. This capability has revolutionized fields such as computer vision, where tasks like object detection and facial recognition have become more accurate and efficient. Recurrent Neural Networks, RNN. Recurrent Neural Networks, RNNs, have transformed the way we handle sequential data, such as time series or natural language. By maintaining a form of memory, RNNs can capture temporal dependencies, enabling applications like language translation and speech recognition. These networks have paved the way for advancements in conversational AI, where understanding context and nuance is paramount. Core structure of a deep neural network. A deep neural network comprises three main components: the input layer, hidden layers, and the output layer. The input layer receives raw data, such as images or text. The hidden layers consist of multiple layers where data undergoes transformations through interconnected neurons. Each neuron processes weighted inputs, applies an activation function, and forwards the output to the subsequent layer. Finally, the output layer generates the final prediction, such as a classification result. This structured approach enables deep neural networks to learn complex patterns and make informed predictions. Types of deep learning models. Let's discuss the various types of deep learning models. Feed-forward neural networks, FNNs, the simplest neural network architecture where data flows unidirectional from input to output layers, commonly used for tasks like image classification and regression. Convolutional neural networks, CNNs, tailored for structured grid data, particularly images. They utilize convolutional operations to learn spatial features, excelling in image recognition, video analysis, and medical imaging. Recurrent Neural Networks, RNNs. Designed for sequential data, RNNs have feedback loops that allow them to retain information from previous inputs. They are effective in language modeling, speech recognition, and machine translation, with variants like LSTM and GRU addressing long-term dependencies. Transformers, a groundbreaking architecture in natural language processing that employs self-attention mechanisms to prioritize input data based on context. Transformers facilitate parallel processing, enhancing performance in tasks such as language translation, text summarization, and conversational agents, with notable models including BERT and GPT. Generative Adversarial Networks, GANs. Comprising two competing networks, a generator and a discriminator, GANs are used to create realistic data samples, such as images, and are effective in image transformation and data augmentation. Autoencoders. These networks learn efficient data representations through unsupervised learning, consisting of an encoder that compresses data and a decoder that reconstructs it. Applications include dimensionality reduction, anomaly detection, and data denoising. Graph Neural Networks, GNNs. Designed for graph-structured data, GNNs learn embeddings based on node features and connectivity patterns, applicable in social network analysis, recommendation systems, and drug discovery. Reinforcement learning models. These models train agents to make decisions through a reward and penalty system, integrating deep learning with reinforcement learning principles. Examples include Deep Q networks, DQN, and Proximal Policy Optimization, PPO, used in game playing, robotic control, and optimization challenges. Applications of deep learning. Now we'll look at how deep learning is applied across various fields. Image recognition. Image recognition involves identifying and classifying objects in images, with facial recognition leveraging deep learning to detect human faces. In medical imaging, algorithms analyze X-rays, MRIs, and CT scans to accurately identify diseases, aiding healthcare professionals in diagnostics. Natural language processing, NLP. Natural language processing focuses on enabling computers to understand and generate human language. Key applications include chatbots for automated customer support and translation services, utilizing deep learning methods like transformers to analyze context and semantics. Speech recognition technology. Speech recognition technology converts spoken language into text by analyzing audio signals. Voice assistants such as Alexa, Google Assistant, and Siri employ this technology to understand user commands, relying on deep learning to enhance accuracy and adapt to various speech patterns. Recommendation systems. Recommendation systems analyze user preferences to suggest tailored products or content. Utilizing collaborative filtering and content-based filtering, these systems enhance user experience on platforms like Netflix and Amazon by predicting user interests. Robotics. Robotics encompasses the design and operation of robots, integrating deep learning to improve automation and decision-making. Robots use sensors to perceive their surroundings and learn from experiences, with applications ranging from manufacturing to healthcare, finance, and fraud detection. In finance, deep learning is applied for predictive analytics, risk assessment, and fraud detection. Algorithms analyze transaction patterns to identify suspicious activities in real time, adapting to new fraud patterns and enhancing security in financial transactions. Key component of deep learning. Neural networks, the backbone of deep learning. These structures mimic the human brain with interconnected neurons organized into layers. Layers. Input layer. Accepts raw data. Hidden layers. Intermediate layers that process inputs, including fully connected, dense layers. Each neuron connects to all neurons in the previous layer. Convolutional layers, CNNs, focused on image and spatial data, applying filters to learn hierarchical features. Recurrent layers, RNNs, handle sequential data with loops that maintain memory of prior inputs. Transformer layers, utilize self-attention mechanisms, particularly effective in natural language processing. Output layer, produces final predictions or outputs. Neurons, nodes, the basic units that perform computations through weighted sums, biases, and activation functions. Weights and biases. Weights, parameters that determine connection strength, adjusted during training. Biases, enhance flexibility in learning by being added to the weighted sum. Activation functions, introduce nonlinearity to the model, enabling it to learn complex patterns. Common examples include sigmoid, Tarn, and ReLU. Loss function, quantifies the difference between predicted and actual outputs, guiding the training process to minimize errors. Examples include mean squared error and cross-entropy loss. Optimizer, algorithms that update weights and biases to minimize the loss function. Common methods are stochastic gradient descent, SGD, and advanced variants like ADAM. Backpropagation, the training algorithm that consists of a forward pass, generating output from input, and a backward pass, calculating gradients for weight updates. In summary, deep learning stands at the forefront of artificial intelligence, offering powerful tools for extracting insights from data and driving innovation across various sectors. As research and development continue to advance, the possibilities for deep learning applications are virtually limitless, promising to reshape our understanding of technology and its impact on society. That brings us to the end of this video. Next, we're going to dive into what is an AI model.